As an engineer, or indeed any kind of scientist, it's a good idea sometimes to sit down, pour yourself a cup of tea, and take a hard look at the things around you to see whether they have anything to do with your own work, even though at first sight they may not. Take this teapot, for example. Why is it the shape that it is? And is it the best shape for a teapot? Well, I'd like to show you the first teapot that was ever designed. You may think it was centuries old, but it isn't. It was designed in 1971. First of all, it's a rather gorgeous thing, isn't it? But that's one affair. Why do I say this is the first teapot ever to be designed? Well, let's look again at our old-fashioned teapot and see how we can criticize it. First of all, it holds a mass of tea, and the center of gravity of that mass is anywhere but near your hand, so all the time you're fighting against gravity. Then, if it had been a large teapot, I would have to put my finger under the spout, in fact, to hold the weight at all. You've probably seen ladies do this in large canteens. Then you tend to scald your finger. When it pours with an irregular, floppy sort of flow we call turbulent flow. So let's look at our modern teapot and see whether this behaves in a similar way. Well, first of all, as soon as you pick it up, you realize that the center of gravity is going to be underneath your hand, whether it's in the unpouring position or the pouring position. And when it pours with a nice, pleasant, smooth flow. Whether you pour slowly or whether you really heave it up like that, it still pours nicely. Your first reaction when you pour rapidly like that is to want to put your thumb on the lid to stop it from falling out. But of course it's not going to fall out because it was designed not to. Designed, in fact, to be the right shape. Now, what has teapots to do with my own subject of electric motors? Well, just this. I think that looking at teapots has shown me that for the last few years, when I've been trying to design and develop new kinds of electric motor, all I've been doing is to change their shape. Or put it another way then, can we, simply by looking at shape, change our engineering tactics and make better use of our engineering materials? So let's now take another look at electric motors, simply from the point of view of their shape. Let's see first how it all began. Michael Faraday started with a disc, a copper disc, and a horseshoe magnet, which he put like that. He had brushes to collect the current at the edge of the disc and in the center. Now the next man said, why not put the magnet like that? And then another man said, no, let's put it at the edge like that, and then we can have a series of magnets all the way around. Yet another man said, let's put the magnets on the edge of the disc and make the disc into a cylinder, elongating it axially. They realized that this was going to make rather a large diameter motor, and so they said, well, let's fold the magnets over like that. And now, realizing that they were using the side of the poles rather than the front, they said, well, if you can do that, then you can put the magnets like that. And in this case, you can now put another disc here and then have another set of magnets and so on and make a long machine that way. So engineers between 1830 and 1880 were simply changing the shape of Faraday's disc to try to produce better electric motors and dynamos. In the Science Museum, we can see some of the extraordinary shapes that they came up with. In the same year that Faraday invented his disc dynamo, this machine appeared. And almost at once it produced a step backward, because it was suggested that the alternating current, which produces this flickering light, should be made more like battery current. And so at Ampere's suggestion, a commutator was fitted. The next machine also produced a step backward in a way. They added more magnets and more coils, and now realized that the magnets were heavy things to rotate, so they rotated the coils instead. Despite these steps backward, both these machines started off a topological explosion in which everybody tried all possible arrangements of magnets and conductor to try to make better use of this magic force that Faraday had discovered. Look at this machine, for example. This is the moving part, a sophisticated form of Faraday's disc with windings on it, and a magnet on each side of it. The magnetic field returned via the end pieces. One form of Faraday's disc. This is a more sophisticated version still with more poles. This is the moving disc in the center. and then from this arrangement to one in which the magnets operated on the edge of what was still essentially a disc. Now, when these magnets were upright in that position, it was realized that they would make a machine of very large diameter, rather ungainly, and so the magnets were folded back like that. But then, realizing the amount of space they wasted inside this machine, they went from this arrangement to this one. In this machine of 1870, the horseshoe magnets dipped down in between a whole series of discs. When you look at the size of this mechanism and realize that the output of it was less than 2 kilowatts, then the shape just had to be wrong. One of the difficulties that designers of this period got themselves into was that they believed, quite wrongly, that you made better magnets when you made them long. So they finished up with all this wasted space through using these long magnets. And they made the same mistake with the previous machine, although in this case the magnets were arranged axially. But again, notice the long length of horseshoe magnet. But to appreciate the lengths that they really would go to, come and have a look at this next machine. Nearly 4 feet of electromagnet, and nearly all of it wasted. You see, the magnetic field generated by the coils at the top is going to leak across here all the way down, and very little of it will reach the base. Such was the obsession about 1880, which is the date of this machine, with magnetic length. Indeed, one author is on record as having said that it was always a good idea to let the magnetic flux have a good run at the air gap. But if you can forget all this top structure and concentrate on the business end, then the idea of having a pole at one side and an opposite pole at the other is not very different from the shape which 20 years later was to become the parent of the modern machine. This generator of 1900 has a pole at the top, a short pole, and a pole underneath. And the magnetic flux is returned by an all-embracing magnetic circuit around the outside. As soon as they'd done that, they realized they could put another pole at this side and another one here and make this rectangle become a circle. And once that circular shape with a magnetic circuit around the outside had been designed, then it did not change fundamentally for over 70 years. Here are 2 electric motors. This one built in 1914 and this one 50 years later. Now, in the intervening time, new developments in insulating materials for the electric wire and new magnetic materials for the magnetic poles have resulted, together with an increase in the cooling facilities in the small machine, have enabled engineers to produce this dramatic increase in the power available from a given size of motor. But inside, the shape of the 2 machines is the same. So as far as our modern electric motors is concerned, they're rather like our everyday teapots. They have evolved since 1880 rather than being designed. Each so-called new design has really been a copy of the previous one with a little addition. But suppose that out of curiosity or simply for fun, we decided to change the shape entirely, just to see what happened. Suppose we were to take our evolved cylindrical shape and do something fairly drastic to it, like slitting it open along one side and unrolling it. Then what have we done? It looks as if we might have produced straight line motion instead of the rotary motion we had before. And when we build a machine that looks exactly like that flat one, as this one is, then we shall find that we have done just that. Straight line propulsion. Man has thought himself superior to nature because he invented the wheel. And the wheel has certainly dominated his thinking in engineering through the centuries. But here is motion without a wheel in sight, linear motion. And there's a bonus to be had. If I increase the current to this machine, then I get lift as well as propulsion. And when I let go of the sheet, it simply flies through the air. Propulsion without wheels and without physical contact. Now, of course, there are all sorts of interesting possibilities for this kind of motion. Here's one of them. A Martian war machine inspired by H.G. Wells's War of the Worlds. When switched on, this machine will levitate itself above this aluminium sheet and also propel itself along. Switch on. Perhaps that's a bit way out at present, maybe the year 2000. But what is concerning us seriously at this time is the possibility of using the same idea, but for guidance along a track, for the possibility of high-speed travel. So let's now look at a levitation system which is only allowed to move in one direction. When this aluminium plate is lifted over this coil system, it will be seen to be free to move in this direction only. The only force resisting the motion is that of air friction, and at this kind of speed there's very little of that. Now once you're clear of the ground, there are only three practical methods that I know by which you may propel yourself along. First of all, you can, as it were, swim through the air. When this has been engineered, we call it an air screw. Of course, this involves a return to wheels with all their associated noise and atmospheric disturbance, but nevertheless, it's a method. But returning to a purely linear device, this one is called a moon rocket. I'll light it first and levitate it when it goes. Crikey. Well, you have something there on film that we hadn't thought of. Yes. Well, we'd better try that one again. I've only got one more rocket, I'm afraid, so I'd better make sure that this one is going to be screwed down a bit more carefully. I hope this one will be all right. All right, let's try again. Well, in an age when we think about pollution, I think you'll agree that this is not on. But a linear motor, of course, is another matter. And this small single-sided linear motor I'm going to use in conjunction with the levitation to produce what it looks at first sight to be an ideal system. It's got to have its own little aluminium strip to push against. So I switch the motor on, and then the levitation. See that again? The motor is still running. There's still some smoke coming from the motor, but that's not intended. It's just because it's a very small machine. And talking of scaling up, unfortunately, the levitation system doesn't readily scale up, because a full-size one would be too expensive in terms of power input and in terms of track cost. But the air cushion principle, which was invented by Sir Christopher Cockerell for hovercraft, can be married to the linear motor to produce what is called a tracked hovercraft. This is no model. This is the real thing. An air-cushioned vehicle running on a concrete track in Cambridgeshire. This vehicle is driven by a linear motor which is designed for speeds up to 150 miles an hour. Nearly 2 miles of track, so flat and straight that the eye can detect no flaws, is an impressive sight in itself. and this is the motor that drives it in course of construction. Coils are being dropped into slots in a laminated steel core, and the whole motor is about 12 feet long. I'm going to show you just one or two of the problems that are associated with trying to make a high-speed linear motor. This block represents the iron part of the motor, or its magnetic circuit. And it's into the slots of this that we're going to put the electric windings. We might decide to put one in there and one in there, so as to make this a north pole and this a south. The question is, what fixes the speed of travel of the field? Well, if you're feeding the coils from 50 cycles per second supply, then the field will travel from there to there in a 50th of a second. And so you can work out the speed. And you see that the speed fixes the length of the coils. But we're not going to leave all these slots empty in between, because that would be a waste of good space. So we're going to fill them up like this with coils carrying different phases of current as indicated by the colors. Try and fill up each slot. And now it's becoming increasingly difficult to get this end into the slot. This end will go in all right, but this one, you see, is getting very tight indeed, because we're building up a bunch of end windings there. And this is a great drawback, because this part of the current is the useful bit, producing the thrust. This part is just waste. Not only is it waste, but it produces a magnetic field of its own, which does nothing except waste your applied voltage. Now, what length of coil would you need to have to produce a traveling magnetic field at 250 miles an hour? The answer turns out to be 4'6". So can you just imagine how these problems would be magnified when you have to deal with coils 4'6" long? You'd be putting one end in a slot over there and the other one 4'6" away over there. And then the next coil, and so on. And this end winding would have built up to something quite impossible by the time you'd filled all these slots. And that's as far as the electric circuit's concerned. Magnetically, all the magnetic flux through these teeth has got to find its way back up the core, and so the core has to be very deep. And so it seemed for a long time as though it was going to be absolutely impossible to design a 250 mile an hour motor to be fed directly from the mains, and yet not to use the mains was going to be very expensive. And then we started to think about shape first and the motor afterwards. And we realized that all the motors we'd been making could be represented by a shape model, if you like, of that kind, showing that the magnetic circuits in red are in vertical planes, the electric circuits, or the coils, in horizontal planes, as shown by the black lines, and then said, suppose we were to change that radically. Suppose we were to turn the plane of the electric circuits through 90 degrees and make a model like that, in which the electric circuits were now in this vertical plane. Now let's see what that's done for the system. In particular, let's see what it means in relation to these small coils. Originally, these coils were in horizontal planes. Now I'm going to replace them in vertical planes, like this. And at once you see that I can have as many coils in one pole pitch as I like without the ends interfering with each other in any way. So this was obviously a good change to make. Well, we made a motor like this and found that we made it worse. When we examined why, we found that the end windings now of the coils were producing more magnetic leakage than before. And the main magnetic field still had to thread its weary way along a very large chunk of steel. So the system was uneconomical. But at least we got this far. We knew how to make it worse. And so it ought to be fairly obvious how to make it better. And we said, if turning the electric circuit through a right angle into this plane has made it worse, then we chose the wrong circuit. We should have turned the magnetic circuit into this plane and left the electric circuit horizontal as it was before. Now, turning the magnetic circuit through a right angle means that we should have had another row of magnets along here and sent all the magnetic field from one side across, sideways into the other. Now, without going too deeply into the glories of these transverse flux machines, as we call them, I'll just show you one such machine and some of the things that it can do. The magnetic arrangement is very simple. It's just a row of horseshoe magnets arranged sideways and single coils magnetizing them. The phase of the current in this coil is ahead of the phase in this one and that one and so on, so you get a phase progression and a traveling field. Watch what happens when I switch it on. It lifts, it propels, it's stable sideways, twist. See how rapidly it recovers when you disturb it. And you haven't really seen electromagnetic levitation until I turn up the current to its full value. And then see what happens. This is a truly amazing machine. It's as if there were some kind of a magnetic groove along which this will travel. It's stable in all three axes, both rotationally and translationally, and it will propel itself as well. Let's just see it again. This is a scale model of a high-speed transport system using a transverse flux motor. Inside the track, there is a row of horseshoe magnets arranged sideways, each with its own magnetizing coil. But in this case, the vehicle itself switches on the track as it needs it ahead of itself by passing over a series of photoelectric cells. We don't yet know how good this system would be if it were scaled up to full size. But if it were good, then we would indeed be looking at the high-speed transport system of the future. Perhaps it's time to go and have another cup of tea, because it was, after all, a teapot which set us out on this fascinating scientific journey. It's been a journey in which we've studied shape, and studying shape can be a profitable exercise for almost any engineer.